Okay, so this is our presentation on the Naphtha cracker control system with myself, Timothy Perry Mills, Kyle Dupre, and Sean Mayfield. Our main objectives of this presentation is to summarize our control strategy, show the PID diagram, review and discuss the results, and do a demo of our final control strategy working in Simulink.
Okay, and now I'd like to go over our control strategies with our 4 different controllers that we implemented. The first controller that we implemented was a feedback controller that responded to the reactor temperature fluctuations and changed the fuel valve position to correct it to a set point of around 800 degrees. We used a PID controller to achieve this using reverse action, and we used controller parameters that were used or obtained using Ziegler-Nichols tuning rules. To do this, we performed an identification test by increasing the fuel valve position and seeing how the reactor temperature responded. By doing so, we were able to obtain a first order plus delay time model for the reactor temperature response with a gain of 3.3, a time constant of 35 minutes, and a delay of 18.5 minutes. Using this model, we obtained controller tuning parameters of a gain of 0.685, a integral time constant of 37.1, and a derivative time constant of 9.275. For the next controller, there was another controller that was summed together to give output to the fuel valve. This one was a feed-forward controller. To implement this, we needed to obtain a model of how the reactor temperature responded to ambient temperature changes, as this was our disturbance. After obtaining this model, we were able to get a rough model of disturbance response of a gain of 1, a time constant of 36 minutes, and a delay of 6 minutes. Because the time constant was very similar to that of the process, we had no lead lag term and only gain and delay terms for the feed forward control transfer function. So for our air valve controller, we had a feedback controller that responded to reactor temperature similar to the fuel valve controller, and it changed the valve position of the air valve to correct to the set point temperature. Done using a PID controller that used direct action and tuned using Ziegler-Nichols tuning rules as well. For this identification test, we decreased the air valve position to get a temperature increase response. And we got a first order plus delay time model with a gain of negative 1.44, a time constant of 44.4 minutes, and delay of 18.2 minutes. Using this model, we got controller parameters with a controller gain of 0.285, an integral time constant of 34.95, and a derivative time constant of 9.275. And our final control that we implemented was on the air valve as well, but this was a feedback controller that responded to changes in excess oxygen by adjusting our air valve position. We wanted to maintain this at a level above a minimum of 9% excess at all times. Doing this, we use a proportional integral controller with no derivative action, and we use a low controller gain of 0.05 to avoid instability and an integral time constant of 1.
So here we have the PID diagram of our control system. First, we'll start with the temperature controller 1 control loop. So getting signal from the thermostat to the temperature transmitter from the reactor, going to temperature control 1. Then we also have input from ambient temperature to the ambient temperature transmitter, which goes to temperature control 2. These two signals are then summed and converted to a pneumatic signal to valve 2. Then we have our O2 feedback loop. We have the O2 sensor signal going to the O2 transmitter, then to the O2 controller. And we have a temperature controller 3, which takes reactor temperature signal from the temperature transmitter to temperature control 3. These two signals are summed and set as one pneumatic signal to valve 1, which controls the airflow.
All right, so after running the controller for 1,440 minutes, which was to simulate 1 day of the plant running, we got a total profit of $25,650. And when comparing that to the maximum of $28,800, we achieved about 90% of that maximum profit. And then when going back to our controls and our constraints, we had an average excess oxygen of about 10.02% and an average reactor temperature of about 800 degrees exactly, which both fall well within our constraints. However, one thing to note before I show you the graph itself is that the control loops seem to give sudden spikes in both reactor temperature and excess oxygen, which can be seen in these 5 points right here on the reactor temperature versus time graph there. And then we have some that are a little harder to see due to the noise generated in the oxygen, excess oxygen. But both did show consistently right around 10% as our average, which is above the 9% minimum there. And there are a few reasons as to why we could have had those spikes. And so just to reiterate again, the response to those sharp changes in ambient temperature had the least mitigation, which will show what the ambient temperature spikes are talking about later. And then the averages of these control variables were within our constraints, but did have those deviations, which could possibly be improved. But after looking at other optionals, ratio controller was not viable just to how sudden the spikes were, and cascade control could be used, but due to the sudden and high change in ambient temperature, which resulted in a sudden and high change in furnace temperature, that high initial error would lead to a integral control inside of the PI controller, which has a very high reset windup, which would cause great overshoot, essentially creating the exact same problem that we would try to mitigate with cascade control. But for that, we'll move on to the actual Simulink diagram itself.
Okay, so here we have our control system in Simulink. After running, you can see temperature and our reactor temperature. The reactor temperature stays around the set point of 800 within about 3 degrees. And you can see the spikes that we were talking about earlier, which can be correlated to the ambient temperature spikes. And if we look at the excess O2 readout, we can see that it stays around 10% with some spikes that are related to ambient temperature with a delay.
All right. Thank you so much. This concludes our presentation on our control system.